Well, good afternoon, everybody, and I want to welcome you to the Instituto de Matemáticas del UNAM and to this lecture series on interactions on geometry and probability. We are very happy to welcome Govind Menon from Brown University and Dominique Inauen from Leipzig University. Today, we are going to start with Govind's lecture, and the floor is all yours. Thank you.
So, first of all, thank you very much. I would like to express my thanks to Carlos, to Sarai, and to Laura, who's not here, for arranging these lectures. A couple of years ago, I kind of made my first mathematical visit to CIMAT in Guanajuato. It was just like an absolute delight to present a collection of ideas. And in a sense, very much, my goals over here are in that sense rather selfish. I want to share with you a collection of ideas where in some sense what we're really trying to ask is what's the role of probability in these theorems. So the core of our lectures jointly between me and Dominic are a collection of theorems, I mean two theorems, in some sense maybe even just one theorem, the Nash embedding theorems. And I didn't know anything about these theorems until about 7 or 8 years ago. I'm an applied mathematician. Most of my work is basically on finding models. The question I ask myself all the time is, what is a good model? And that's the question I'm going to ask throughout these lectures. I want to introduce you today to kind of like what are embedding theorems, who uses them, and to kind of convince you over the next few lectures that somehow, despite the fact that probability theory was not traditionally used for the study of these theorems, that probability theory kind of seems to play a very important part in these theorems. So I also just kind of like, just a couple of words. So somehow for me, the central perspective in these problems has really been somehow the sense that embedding has really kind of got an information theoretic core that feels philosophical, and I'm going to try to make it concrete. And so it's really for me a kind of personal regret that Mario Diaz is not here, so I'd really like to dedicate these talks to his memory. So today what I would like to do is to kind of tell you what are embedding theorems and to focus on kind of, let's say, the simplest type of idea within the space where I can begin to see probability theory showing up. So in embedding theorems and embedding problems, what we're really trying to do is to distinguish between a geometric problem or a geometric property which is defined, let's say, on abstract grounds, versus kind of realizing this geometry in a very concrete way. And so I'll focus on 3 distinct examples, and today's talk is really going to be on the discrete case. Of finite metric spaces. So really just a collection of points. So imagine that you're given so I'm given some metric space K, which for me now is just a collection, a finite collection of points. So what are you given? So you're given collection of points. So let me just label them as points x in K. And you're given pairwise distances. Okay, so that means that between any 2 points within the set, you've got a distance d of xy. The distance is positive and satisfies the triangle inequality. So this is just an abstract construct, a set with a distance on it. So what's an embedding? So what we want is a mapping of the set into a familiar space. So, you could have a, what's your familiar space, maybe, some kind of fancy manifold or something. But for us, a familiar space is just going to be into Euclidean space. So what we want is a mapping you want this mapping to be 1-to-1. And what you want is a mapping such that the distance for all pairs okay. So it's a very simply stated problem. This is the given distance. And this is the distance in RQ, Euclidean distance. Okay. So I'm going to give you another variant of this, which is not that different from it. Wow, these are amazing blackboards. I love this. Okay, so here's a kind of slightly, a kind of variant on this. So in this case, again, I'm going to be given an abstract space. So my abstract space is a finite space, a graph. Okay, so these are the vertices. Those are the edges. So some picture of this sort is, for example, what you may think about when you're given a graph. And so what's going to happen for us is it's a slight variant of that problem. So I'm given my finite set over here, but my finite set in some sense has a discrete topology, so it makes it a graph. So it's got a little bit more information than just the distances. And so you're given and we're going to have a function. Okay, so this is a weight on each edge. So for example, if that's my graph, let me denote that edge by E. And just to I'm going to give the graph some sort of orientation. The orientation is going to be completely irrelevant, but I just want to kind of introduce the orientation so that I take the two vertices which are adjacent to this edge, and I state the kind of underlying equations using this language. And so what we want, so here's what we want. We want a mapping. So we want to realize our graph in a kind of concrete way. So what I want is a map. So actually, when I've drawn this, I've actually drawn an embedding of my graph. So somehow you have to imagine an abstract graph. And we've got a mapping. So each vertex is now tagged with a point in RQ. And now what we want is so for each edge, you want, again, the same condition. So this is the, let's say, given length. Or I called it the weight, so let's say given length. And over here, this is the length in RQ. So the question that we're interested in is really just the solution, finding solutions to this system of equations, of finite collections of equations. So these two problems are problems for discrete spaces, but our work this week, most of it is actually going to be on a more sophisticated, well, if not more sophisticated, but definitely a kind of continuous geometry. Ah, lovely. Example 3 is the embedding problem Okay, so I should be using the word isometric embedding in each case. So this is the problem that's really been motivating us, but in a sense, I feel like the probabilistic ideas actually and independent applications are apparent in, or kind of perhaps simpler to see first in those discrete examples. And so over here, what's given to us so you're given a smooth manifold. So the differentiable structure of the manifold is fixed. So given a manifold M, let's say with n dimension, and you're given a metric on this manifold. Okay, so you're given a notion of length on this manifold. And in this case, so this is the part that Dominic is going to kind of describe in just a second. So let me kind of give you a very, very concrete example of this. Okay, so let me write it out and then let me give you an example of this. So what we want now what we're looking for is a one-to-one mapping from this manifold into our Q. And you want this mapping, let me state it somewhat vaguely, as being sufficiently smooth. And this condition of equality of lengths, I'm going to write out in a slightly cryptic form and then give you an example so that you have a feeling for it. I'm going to call it. So this is the pullback metric. And let's just make that concrete in a second. And this is given. So in each of these problems, what you're given is an abstract object with an abstract notion of length. And what we're trying to do in this embedding problem is to realize this abstract object in a kind of very, very concrete way. So this is actually a system of partial differential equations. And let me kind of give you a very, very concrete example of this, which is already very interesting. And you know, already where there are plenty of open questions. So let me kind of give you an example of this because it's of a different level of sophistication from the ones above. So here's an example. Take as our manifold just the two-dimensional torus. Okay, so the two-dimensional torus is defined on abstract grounds. Okay, so it's really, that's R2. And what we do is we take this region, and what we've done is we've identified the edges. So that's how you make the torus. And now what we're trying to do is we're looking for a mapping of this torus into three-dimensional space. So something like that. But the condition is that the length that you're given over here, so over here we take M is, so the manifold I've described, and let's say the G is simply the identity. So a metric is, you can think about it as a kind of it's a positive definite, okay, so okay, I don't want to do, so let's just think about the metric, so let's just think about the standard notion of length that you're given over here in R2. And what happens over here is that if you take these to be your, let's say, your unit vectors, then these unit vectors are going to give you over here some. So each of these guys is giving you a tangent vector here, manifold over here. And so the system of equations of this sort, so let me write out the derivative for mapping as being, so, you know, I'm going from, so I'm looking over here for a mapping from T2 into R3. So my U has three components. So, you know, think about it as a a matrix which is 2 by 3, where in the first column you have u differentiate in the first direction, u differentiate in the second direction. And this equation over here now becomes the quadratic partial differential equation again, the condition over here is the length measured in R3, and this is, or somehow formally, this is the length measured in R3, this is the given length. Okay, so of course, when you're doing things with manifold, you're looking at kind of the length associated tangent vectors. But you see that the common character of these three problems is one of kind of the abstract object given with length, and then you're kind of realizing it in R3 in a particular way. So these three problems seem to have absolutely no probability theory in them. I'm not going to describe the manifold theorems. That's coming in the talk by Dominic in just a second. But I want to tell you a little bit about kind of the scientific applications of these theorems to give you a sense about why one would begin to believe that probability theory is natural in these problems. The statement of the problems clear? Okay. Okay. So let me tell you why I began to be interested in these problems. Why do that? So is it okay if I write on this board? It's all fine, right? Okay. So at a kind of loose sense, the main question is, in some sense, the type of question that we're asking is, the question that I'm trying to give meaning to is this problem. What does a typical isometric embedding look like? So you've got, in principle, these equations. So what you're trying to do is, in some sense, to put down natural probability measures on the space of solutions to these equations. So the equations don't seem to have probability in them, but there are various applications where somehow you need to encounter this question. So rather than do this, let me kind of give you a sense of where this kind of notion of typicality is coming from in this problem, by just giving you a simple example of where people who uses graph embeddings, and why would you think about this problem from probabilistic standpoints? So let me just do sample applications. So one of these, which is super simple to explain for graph embeddings, one of the contexts in which this one shows up quite a lot is what I will call conformational diffusion of molecules. So I encountered this problem maybe like 2010 or so. I was kind of working on kind of what's called protein folding at the time. And as I was trying to understand those problems, at some point I was like, okay, simplest possible mathematical description, or the simplest possible mathematical description. And a fairly typical thing is something like this. So you take, so let me just draw pictures. Let me take a simple graph, something like this, a quadrilateral, and all the lengths are equal to 1. And one of the things that you notice about this, this particular linkage is that, of course, this linkage may exist in widely different configurations. So you can move this guy around in a whole bunch of different ways while preserving the lengths. Okay? So it turns out that this understanding of kind of what exactly is the way, what is the kind of the shape of the graph as it's embedded, ends up being a kind of bottleneck in all sorts of computational schemes for designing, for figuring out kind of where molecules are going in space. So there's a lot of effort from computational physicists, and when you look at these efforts, of computational physics, they build kind of force laws one on top of another. You realize at some point that there's a kind of core mathematical problem in here, and in some sense, the reason you kind of want to focus on this core mathematical problem is that it's minimal, right? So somehow if you just look at the shape of a graph, how a graph is sitting in space, you tend to believe that it's such a kind of, it's a problem with such a simple description that there must be some sort of natural way of trying to understand how to describe the conformational diffusion of these molecules. So chemists are actually more clever than that. It turns out that there are special molecules, so cyclohexane. So I don't, Maria and Amelia may be like way back in your distant past, but there are these special molecules, which exist in different shapes. And one of the most interesting things in chemistry is kind of understanding how it goes between these different conformations. So there are perfectly simple geometries, so you can kind of imagine coming up with kind of simple kind of elementary geometries, these linkages, which do counterintuitive things. Okay, so this is one place where as soon as you look at the context, right? So if you're doing chemistry, you're always working in a thermal environment. And so despite the fact that when you state the problem in this way, there doesn't seem to be any probability theory in it, when you actually try to look at the problem this way, you realize that, well, actually, you do want to figure out kind of what's natural, typical shape of such molecules. There's another kind of picture that shows up. And this is with the graph embedding problems. Okay, so this is one picture. So one of the places where graph embedding shows up a lot is in problems in theoretical computer science. And over here, the problem becomes of a very different sort. So when you think about chemistry, like, you kind of like I would say our level of understanding is that we're really looking at simple molecules and trying to get the geometry right. But it turns out for computer science, one of the typical things they care about is stuff like minimum dimension for which an embedding exists. Sorry, I'm using the word embedding, but I'm always kind of thinking about isometric embeddings. So it turns out that one of the things that happens in these problems, and I think this is going to come out more in the next lecture, is that one of the things that happens in these problems is that you have to let this dimension of the ambient space be a little bit fluid. So you may have an embedding of a graph into a particular dimension, but maybe you don't have an embedding of a graph into kind of, you may not have an embedding of a graph into a small dimension. So for example, if you just think about the triangle, you cannot embed a triangle into R1, you can definitely embed a triangle into R2, right? So somehow there is an existence problem, and somehow you're trying to understand what are the properties of your graph which will actually give rise to whether an embedding exists or not. So, yeah.
Before you were talking about some conditions about your embedding.
Yeah.
So how are those conditions? Yes. You were talking about some conditions before for your embeddings.
Yeah.
So how are those conditions inspired from these applications you are mentioning?
So that will come out more in Dominic's talk. So we will kind of talk very much about the codimension in these cases. With these examples with graph embedding, I still see this as what I'm doing. I see this really as proof of concept. I think the thing that I really want to show you with graph embeddings is that we can treat all of these problems in a unified way. And I kind of want to give you one of the core heuristics, which is why I'm doing the graph embedding problem today. But most of our interests are actually in this problem. And in this problem, the conditions are on the smoothness of the metric, the nature of the manifold, and the ambient space Q. So we're not going to do kind of very sophisticated versions of that, but the conditions are really related to the smoothness of the embedding. And those are very closely tied to actual practical applications, which I'll just give you one example in just a second. Yeah.
So, but the other question is, you were, the very first thing you said, in this first part, there is no probability.
Yeah.
And then you are mentioning here that how probability turns up. Can you repeat that, please?
So I think over here, conformational diffusion. Do you accept that this is probability? The shape of the molecule as it's moving around? The fact that you're living in a thermal environment? Okay, so that's probability. Here's another one involving the manifold embedding. So most of our body, the cell walls in your body are membranes, and they're existing in a thermal environment. So again, there's kind of like not just you want the manifold embedding, but your embedding you can imagine is going to fluctuate as the shape of this guy fluctuates. So that's another example where probability shows up. Though that's not going to be, okay, I mean, that's kind of like two answers to your questions. For this one on minimum dimension, actually, I don't have a good answer for that. So yeah, this one, I'm kind of not quite where I have a good answer on that. Okay. Can you hold off? Like most of our lectures are actually going to be in that direction. Okay, or anything more? You're okay? Yes. Okay. No, I wasn't sure. Sorry, I'm just getting warmed up. I'm waking up from lunch. Okay. So let me tell you actually, since, let me tell you where I really began with these problems. So the technical core, part of the technical core in these lectures is really going to be somehow understanding Nash's work and understanding kind of what the existence theory is for these PDs, existence and regularity. And one of the reasons this problem has kind of become so important in the past 10 years, or past 10 years, let's say, is a third scientific application. And this has actually apparently nothing to do with embedding, but it's a major open scientific problem, and it's related to what's called turbulence in fluids. Okay? So I've written down one PD on the board. It's a PD from geometry. It's a PD that just describes equality of lengths. I'm going to write out another system of PD, and this is the PD that describes ideal fluid flows. So ideal means without viscosity. Incompressible. Or so this is perhaps the first system of PDs written down in the mid-1700s. And so I'm going to use U again. So let me think about a system of equations defined on the torus. So that's space, that's time. And we have a and it's been known for the longest time that the motion of the fluid, so this is the velocity field of the fluid, this is the pressure field of the fluid, is described by a system of partial differential equations of the following sort. Pressure is a scalar. Yes, absolutely. Sorry about that. Okay. So one of the important properties of this physical system, so what is this physical system? This physical system is Newton's law. So what happened is, I mean, in the early years of kind of mathematical analysis, one of the things that Euler did was to kind of write out what is the description for continua? How do you apply Newton's law to continua? And it turns out that all you have to do is to describe the velocity field of a all you have to do is to describe a velocity field. And so the left-hand side of this equation is really acceleration. The right-hand side is like the force acting on it. So this is really just F is equal to ma. And this is a geometric restriction which works for fluids like water and air, which says that you've got conservation of mass. So this equation is the physical principle of conservation of momentum. And this is the physical principle of conservation of mass. Now, what you see on the board in some sense is the true traditional sources of partial differential equations in mathematics. So partial differential equations in mathematics, one of the kind of fundamental sources of partial differential equations in mathematics is geometry. And over here is physics. So somehow you've got the PDE of mathematical physics and you've got the PDE of geometry. So, when looking at the geometric problem, we don't have any time in it. We are just thinking about kind of finding a particular solution which is satisfying a system of constraints. But when you're studying kind of the equations coming from physics, you have typically some sort of experimental context. And it was very traditional when studying partial differential equations of this nature that what you do is you focus on the initial value problem. So you're given the partial differential equations, and you're also given, let's say, the initial condition, so u0 of x. So the typical type of theorem you want to prove in partial differential equations of this sort, so going back, let's say, to the 1950s and Laray's work, is to say that if I'm given my initial data in a particular function space, or just given my initial data, let's say informally, I want to find solutions to the PDE with this given initial condition. And the core physical principles, so somehow you've got conservation of momentum, conservation of mass. We've assumed that it's an ideal fluid, so the energy can't go anywhere. It's just contained within your system. The natural thing to kind of expect in this problem was that you would have conservation of energy. So one of the interesting things about ideal fluid flow, and this kind of use of the word turbulence, is that when you look at real fluids, they do all sorts of crazy complicated things. So there are very good reasons to believe that these are the right equations. And there are very good reasons to believe that when you look at fluid flow, so for example, in a wind tunnel, right, so kind of very benchmark fluid mechanics experiment, that what you see coming out of the fluid flow is very regular properties. So it turns out that in this case, what we expect is actually, despite the fact that it says you've got conservation of energy, what actually happens is that the fluid flow is kind of sufficiently rough. If it's sufficiently rough, it will lose energy. So this idea, this kind of physical idea, was studied in the 1940s, on one hand by Kolmogorov, the great mathematician, but on the other hand also by physicists, in particular Lars Onsager. And one of the things that Onsager discovered in a very kind of brief note in the 1940s is a kind of remarkable observation. This is well before the theory of weak solutions to PDE and things of that nature. So one of the things Onsager kind of conjectured, or kind of like just stated in his paper, is, well, if solutions to this equation are rough, and rough over here means that it is C0 1/3 minus. There's a magic exponent. So somehow if you find solutions to this PDE, which are, so what I mean over here is that we've got a function which is defined in space and time. So we are really looking at continuous functions. We integrate by parts this PDE, so we've got a notion of weak solution to this equation. So this, I mean, we're not going to focus on this equation, but this is, let's say, background to the stuff that's coming in Dominic's talk. So somehow there was a kind of an absence of mathematical methods to construct counterintuitive or to construct solutions to this PDE with this kind of critical roughness. So the kind of strange coincidence or kind of remarkable kind of theorems that were proved by Delelis and Sekahidi, and then several people after them, late 2010, like around that time, was that somehow it became possible to construct non-trivial solutions to this PDE by going back to Nash's methods from the 1950s on this PDE. So for somebody who comes from PDE, this is very, very strange because we typically think about the PDEs of physics and people of PDE of geometry as being from completely different categories. But somehow the techniques that we used over here were useful for this PDE. So this world of turbulence is a kind of world of mathematical physics. And so in the world of mathematical physics, you're used to kind of thinking about Gibbs measures, concepts of that nature, where again, probability theory is very natural. And so somehow this connection that, here's this class of partial differential equations, here's that class of partial differential equations, and they unite in some ways in techniques. But somehow probability theory is natural in this world, and the kind of story that we're trying to tell you is to kind of explain to you why probability theory would be natural in these problems through that extension. So that's where I got into the game. I had been working on turbulence, these kind of results came out, and I was like, well, we kind of use probability theory over here. And actually, this is why I kind of know some of the people who do Levy processes in the audience, because I was kind of working on vastly simplified versions of this equation where one could kind of construct random solutions to the PDE. And somehow I was like, there has to be some conceptual reason why probability theory is showing up in this problem. And so today I kind of want to show you two key ideas from Nash's proofs at a very, very elementary level, reducing it to the graph embedding problem, and then to conclude with, I think, an open problem on a diffusion that I hope someone in this audience will figure out, okay? So, yeah. Yeah. Wait for the mic. Or speak softly and I can repeat your question. Yeah. Yeah.
Who has the C0 1/3 minus condition?
So the final result over here was obtained by ISAT in, I think, like, I don't know, was it like
I meant, is it U0? Who are you referring? I mean, who is supposed to have this sort of regularity? The U0
so
only.
It's the U has a C0 1/3 regularity, and then you kind of figure out the regularity for the P accordingly. But the C0 1/3, it's typically referred to the velocity field. So, okay, one of the things that's lacking in this talk is actually interesting pictures that show you this stuff. So maybe after this, I can circulate a couple of pictures that show you kind of the C0 alpha stuff for the embeddings and then C0 alpha stuff. So these are really kind of like very, very complicated solutions to the PDE obtained by adding in kind of stuff at rougher and rougher scales. So kind of think about it as some sort of fractal solution to this PDE. That's kind of what we're looking for.
But U is the whole solution. So you're not.
U is the solution. So at each point, and so it's C0 1/3 is the function space in which I'm working. Holder class.
Okay,
right?
you want
and so it's just like,
okay.
you want it, so you, like, there's a, like, in some sense, I really did want to do background, just to kind of give you a flavor for where the kind of ideas are coming from. But to do this, of course, I need to define these spaces, define what I mean by weak solutions to this PDE, and state the theorems precisely, which would take me a little bit too far afield for today.
Thank you.
Okay? Yeah. Okay. So let me kind of cut to the chase. So most of my work these days is actually on AI. Most of my work is really on kind of those theorems, the embedding theorems. I began with this world, and it turns out that when one kind of looks at, so within the mathematics, so in any PDE of this sort, this is a classical, deeply classical mathematical problem, and I think Dominic is going to show you kind of the sequence of results in this area, and all of these results are analysis theorems. Okay, so analysis theorems where, like, person X proved this, person Y proved this, and we've marched forward one by one. What I'm really saying in some level is something just very simple, which is that if you look at the scientific context in which many of these problems arise, it's very natural in the scientific context to kind of see the probability theories being natural. So for example, with the embedding theorems, the place I really think about them is in data clouds. Or, I mean, the people who use embedding theorems are really, again, computer scientists trying to understand how function approximation works. So in the context in which people actually use these theorems, it's very natural to use probability theory. And what we're really trying to do is to find practical pieces, steps in between, which will actually improve these theorems or shed new light on these theorems by using probabilistic methods, okay? So that's the spirit of the stuff. I'm sorry if I'm kind of, not quite communicating kind of sufficient detail at this point. But let me switch to a more concrete kind of tasked with the graph embedding problems, let me reduce to my natural level and show you something quite clear where I hope you can see the probability theory appearing. So, okay. So I want to give you kind of like somehow an idea. It's really not a theorem. It's really just an idea that's really waiting to be exploited. And this idea comes from kind of taking a look at Nash's work and saying, like, can I kind of modify what he's doing, this control scheme that he's doing, to somehow get a stochastic control scheme? And I kind of began with this idea, kind of working with the manifold embedding problem. But I realized that the idea is actually, you know, it's really got, it's much more transparent when I do something simple like graph embedding. So one of the critical words over here is relaxation. And so let me introduce this concept, and then I'll introduce what I mean by stochastic relaxation. Okay, so what we want, so let me go back to the graph embedding problem. So we're given the graph. We're given, let me write out the equations in a slightly different way. So I'm trying to solve this system of algebraic equations, and I've written it out in this way so that it just becomes quadratic equation. So I've really just got a collection, a finite collection of quadratic equations. So so I'm looking for a solution of the system. So I don't know how to find a solution to the system, but the way I'm going to try to find the solution to the system is by beginning with the concept of sub-solutions. Let me write it out this way, so let's be slightly more formal now. A strict subsolution to star is a map, say V, from the vertex set to RQ, such that you've got the graph. You want to make all the lengths equal to a given value. But okay, maybe you don't get all those values. Maybe you've actually shrunk some of the lengths. So the idea over here is going to be the following. Find a diffusion oh, actually, let me, sorry, just a second, answer definition. Sorry, was there a question? Ah, yes, of course. So, the reason I want, yeah, so I either want the square there or I don't want the square there. The reason I actually wrote out the square is because I'm going to use an etho calculation, and it's helpful to have the square in there. So that's the only reason for putting in the squares in there. It also kind of, it really makes it look like a polynomial system of equations, and that kind of simplifies matters. But yeah, you're completely correct. I do want the square in there. Okay. Okay, so here's the idea. And so let me just kind of make a schematic sketch, right? So somehow the way I'm going to think about this is that I want to think about this. There's just a kind of idealistic cartoon, so you see what I'm going to try to do. So somehow I want to imagine that I've got my space of sub-solutions. Okay? And these kind of points over here are where I've got solutions. So somehow you've relaxed all of these inequalities, but when you get to the boundary, or on the boundary, one of the inequalities is saturated, then you want all of the inequalities to be saturated. So you've got a space of sub-solutions. So the space of sub-solutions is non-empty because I can just map everything to 0. So I've definitely got a sub-solution. So my idea is going to be, I want to start out with any sub-solution, V0. And then what I want to do is I want to design a diffusion that's going to take me up. Okay? So the problem is really going to be one, so as I said, I'm an applied mathematician. The question that I ask is, what's a good model? And the problem over here is going to be, how do you design a diffusion that'll start within the space of sub-solutions and take you out towards the space of solutions? So I want to show you the simplest, I want to give you an insight, and I want to give you a theorem. The theorem is going to be absolutely trivial, but I'd still like to show it to you because it kind of captures one of the critical issues that we face, which is how do you design a diffusion in a principled way? So let's do a very, very simple example. Okay, so I can write down the diffusion in absolute detail, show you everything that I'm doing. So I'll take the simplest possible graph, which is a graph with 2 vertices. So my graph is just going to be this. And I've got 2 edges. Let me just call it minus and plus, or okay, let's call it 1 and 2. And I say rho of E is equal to 1. I've just got the graph, 2 points with 1. And what I want is a map. I just want to take the edge and I want to embed it into R. Right. So what we want is a UV to R such that U1 minus U2 is equal to 1. So of course, you know that you can do this, but let's pretend you don't know how to do it, and let's see how we could try to do something like this with probability. Okay? Is the problem clear? Like this is my natural level, okay? I can't do math, which is much harder than this. Okay, so what's the cartoon that I want you to have? Who's the nice chalk? Okay, great. Plus is all recorded for posterity, right? My kids will love this because, in my family I have a reputation as being the clumsy person. Okay, so let me write down an ST, which is going to do this. So let's push that board up. Okay, so what we'll do is consider a diffusion. going to write it out as follows. I've got du1, du2. I'm going to write it out as some matrix A of u, dv1, dv2, where dbi standard So the picture that you want to have is as follows. So there's the real line. I'm going to start out both of my particles at 0. So let's say u1 of 0 is equal to u2 of 0 is equal to 0. So there's my abstract graph. I've mapped these points into initially one point over here. And now it's going to have, or let me make it like, let's say is equal to minus epsilon u2 of 0 is equal to plus epsilon, where epsilon is some small number. So I've started off with 2 points which are very, very close by. And I'm going to introduce a diffusion. And what the diffusion has to do is to get these guys to fluctuate and to push apart. So our game is really going to be, what is this matrix? How are we going to choose this matrix? And how do we know that something like this could ever work? Okay. So the main observation, really in some sense, is just an observation with Ito's formula. So here's an observation. So take any, so I haven't even like, I'm just going to like, let's just assume that our A is a Lipschitz function so that we can do whatever we need to do in terms of our applications of Ito's lemma. But the observation really is the role of the Ito correction in problems of this nature. Okay, so the observation, suppose U1, U2, so suppose solves the above SDE. So we are working, so somehow, okay, so I guess over here I've called it U0 now. So I've started out with a sub-solution, so my length is less than 1. And so what I need to do is to see how the length changes as I solve this SDE. So what you do is you want to see, what you want is U1 minus U2 as t converges to 1 as, let's say, as t goes to infinity, or as t increases. So what you do is, so somehow you have to look at, the basic estimate that you have to do is to look at the rate of change of the length over here. And so what you do is consider this difference. So that's why I put in the square, because this is a nice smooth function. I can apply Ito's formula. And so by Ito's formula, this is going to be and now there's the Ito correction, which ends up being, in this case, now, this is just a martingale term. So, on average, it's going to be 0. The key piece is just kind of observing what happens over here. Okay, so let me just use my boards a little bit more efficiently. Okay, so let me do it over here. Let me just work that out. So I'm going to kind of just introduce a little bit. know what the answer is going to be. I'm going to write it out. Okay, so write it out in the following way. Kind of. So somehow, I mean, what's going to happen, as you can imagine, is this correction term over here is going to correspond to the covariance of the process that we began with. And the calculation in this case actually becomes a little bit cleaner if you work with the covariance associated with that matrix. And the key calculation so let's write this out as du1 plus du2 2. Okay, you need to do a calculation with the etho formula to get this right. And it turns out that what it works out to be is this. So it's a nice concrete calculation. I kind of leave it to the students to kind of check that this all works out. It's really just a good exercise in etho's formula. So the key observation at this point is it really doesn't matter what your matrix is. If you choose a diffusion, the kind of convexity of the quadratic function over here will ensure that you, on average, your length is going to increase. So this matrix, it's a covariance tensor, it's positive definite or positive semi-definite, and this term is always going to be positive. Okay? So this is positive because it's really, you can think about it as it's 1 minus 1, k 1 minus 1. So it's a positive definite matrix because it's covariance, and then it's just two vectors acting on the left and right, so it's really just the differences between these terms, and so this is 0. So somehow, if you want to push up the length, so the idea over here is that, we are trying to design this diffusion. So in order to design this diffusion, we are taking the simplest possible ansatz for the diffusion. And then we just do exactly one calculation, which is really just the most basic calculation that you can do, which is seeing how the length changes under the SDE. And you immediately find that the rate of change of the length is given by something very specific in terms of the k, which is this kind of piece of this matrix. So what's happening is that on average, whatever your diffusion, you're going to be pushed out. And so the design problem in this case becomes, how do you choose this guy given a particular rate condition? So, I'm sorry, let me just take a look at my time. 4 o'clock, 4:02. Sorry, is this calculation clear? I feel like I may have lost people at this point. Kind of okay? Okay. So, let's do it over here. So here's one consequence of this. So define the residual. So, so at each point we've got a subsolution. What I'm doing is looking at my subsolution quantitatively by how much it fails to satisfy the equation. So let me define the residual. Let's say R of U is 1 minus U1 minus U2 squared. Okay, and so one of the things that I find from this calculation is that, let's say dr of u, it's really just the negative of this. So this is going to be a martingale term plus or minus k11 plus k22 minus 2k12 dt. So again, I'm trying to design a diffusion, which is going to get these guys to jiggle, 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 keep moving further and further apart until it becomes exactly equal to 1. And so I can actually, so somehow my design problem I can prescribe by setting this to be whatever rate I want it to be. So choose k such that k11 plus k22 minus 2k12 is equal to, let's say, R of u. So if I can choose a covariance tensor that satisfies this condition, then what I found and now it's an absolutely straightforward theorem from here to say that the residual is going to approach 0 exponentially in time with probability 1. And so you've found a solution to the graph embedding problem. So somehow you have designed a diffusion that's basically going to converge to a graph embedding. So we kind of have this picture of kind of particles kind of jiggling, 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 and moving further and further apart. And every single covariance tensor that satisfies this condition will achieve this. So one of the things that I'm showing you over here is proof of concept of solving the graph embedding problem by running a diffusion of this case in the simplest possible situation, where I'm embedding the simplest possible graph into the simplest possible space. But the key observation over here is really just that the etho correction, if you introduce a diffusion, is always going to push every single length apart. So it turns out that there's actually nothing specific to one dimension over here. What's really happening is that we are trying to make a control theory strategy or a stochastic control strategy, which relies on relaxation and then the kind of pushing out feature. And when we kind of look for our control theory strategy, what we are really reduced to is a condition on the covariance tensor, which is a condition on the covariance tensor involving the length of each edge and whatever your desired rate of convergence to the solution is. So the general principle in the background is actually very similar. So now you kind of just have to generalize this. So you have to kind of look at a fancier diffusion in a higher dimensional space. So you need to include kind of the vectorial nature of the problem. You need to include for the fact that you may have a more complicated graph. So now I'm looking at a kind of more complicated graph. So I've got conditions on every single edge. So I've got a residual on every single edge. And I may be going into kind of a high dimensional space. So kind of the nature of the problem gets a little bit more complicated. But it turns out that essentially the same structure continues. Okay, so the generalization of this problem, okay, so I'm going to have to write it out in a slightly more kind of slightly more complicated vectorial notion. Okay, so here's the generalization. Or okay, let me kind of give you. Sorry, let me give you a kind of summary and then kind of explain the issue. Yes, now what we want is Q. So the equivalent of K is, let me just explain this with a picture. So what actually happens over here is really just complicated bookkeeping. You have to keep track of the vertices, and you have to keep track of the vectorial nature of the problem. And so somehow, let me just make a picture of that. Okay, let's make a. But let's say that the problem that we were trying to solve is a problem for a graph of this nature. And what I've actually got is something where all the lengths are smaller than 1. And what I'm trying to do is to prescribe a diffusion which will push each of these edges out. On every single one of these edges, I'm going to do a calculation of this sort. And I'm going to compute what the etho correction is. Okay, so the bookkeeping is something like this. So, let these points be indexed by x and y related to kind of what the vertices are. And let me kind of refer to kind of the components of the diffusions by an I and j. And so it turns out that what you're looking for is a covariance tensor which has this character. So here x and y are vertices in the graph, and these other two indices are just describing the kind of vectorial nature of the problem. So where once we had a kind of clean 2 by 2 covariance tensor, now we've got this kind of gigantic covariance tensor. Let me just give you a kind of schematic of it. So think of the covariance tensor in the following way. Think about this as, so let's think about the x's going this way, the y's going that way. So the x's and y's are the vertices on my graph. And for each x and y, let me think about a block over here, which is of size q by q. So at this point, what you do is we need to solve so this is the collection of equations I began with. But we're actually at a subsolution. So when I've got a subsolution, I've got something or another way of writing it out is that I've got a residual on every single edge, which is the rho squared of E, or minus this guy. So at each time of my diffusion, I'm going to try to make up by something which will reduce the residual to 0. And the etho correction, so the computation, okay, so let me actually write that down below. So it's actually so you do exactly the same calculation, but on every single edge. And what you find is really just a computation, and I'd be glad to write it up in the notes. Computation of etho correction so on every single edge, you're going to get a martingale term, and you get a correction which is going to be, I'm going to write it out in the following way. So it's going to be K1 through Q, K I of E plus K I E minus of E plus E minus. So in terms of that covariance matrix, what's actually happened is we've got this big covariance matrix. On this big covariance matrix, we've blocked off 2 edges, and associated with the edges, we have the adjacent vertices, which I've called E minus and E plus, And I've got blocks of my covariance tensor. And I'm taking the trace of this plus the trace of that minus the trace of these two pieces. It's a linear condition. You have to compute this condition, but it really comes out of exactly the same elementary idea. So what's happened is we are trying to design a diffusion. In order to design a diffusion, we really just have to prescribe the covariance. Because of the vectorial nature of the problem, the covariance has this kind of big matrix structure. But what's really happened is that the given constraints, the given equations were, so these are the equations that we're trying to solve. Really, these elementary equations which describe equality of edges. And what this has given rise to, that's my warning. What this has given rise to is constraints on K. The linear constraints on K are of the form this. Q E minus E minus residual squared. Yeah. That's equal to residual squared on the edge. So what had initially been equations on the edges that you need to solve has now become constraints on a covariance for one constraint on the covariance for every single edge. So the reason for kind of doing this calculation is to show you that the design problem has actually led to a set of constraints on a covariance. And these constraints have the nature of the constraints of a semi-definite program. So semi-definite programs are one of the fundamental classes of optimization problems. And a semi-definite program has two different parts. So one is a collection of constraints, a collection of linear constraints on a positive definite matrix. And the other one is a cost function that you choose to optimize over this system, a linear cost function. So what I'm telling you over here is the following. I've got an embedding problem, a very simply described embedding problem, which says, here's the graph. Every single edge has to have a particular length. What I'm doing is I'm kind of running an explosion. So I throw all my points in the graph into the origin, and then I let them all jiggle out in space. So they kind of like, you know, my picture is that I've got this guy, and then each of these points keep moving, and my edges are becoming bigger and bigger. So I'm kind of trying to drive this diffusion towards the right lengths. In order to do so, I get to choose the rates at which I converge. And I'm just choosing, you know, constraint to be the residual so that everything is kind of converging with an exponential rate 1. But I have to satisfy, in order to be able to design this diffusion, I must be able to satisfy the constraints of the semi-definite program. So let me tell you what our status is of this. So the kind of thing that we've done with this is really solving, so implementing the scheme numerically. There's a little bit of a hack in terms of kind of the issue that you face is that you've got a semi-definite program. So in fact, there are many possible solutions to this constraint. So there are many different diffusions that may drive you to the end. And I actually don't have a principled answer to that. Even in the really, really simple case of taking one edge and kind of pushing it apart, what happens is that you have to choose a two-dimensional positive definite matrix that satisfies one equation. So you've got 3 independent variables and 1 equation. So in fact, there's an entire set of diffusions which will get you to the graph embedding at exactly the same rate. And I don't quite know how to resolve this. Another problem that we face in practice is that I've cheated a little bit. So what I'm trying to do is I'm trying to make a diffusion that kind of simultaneously, as t goes to infinity, satisfies each of the equations. In practice, actually, you run into trouble. And if you don't design your diffusion carefully, it kind of hits a boundary. One of the lengths gets saturated. And you know, you're kind of like trying to design diffusion, which is kind of going, you know, one of the lengths becomes equal to 1 and it gets locked, and then you kind of have to move the rest of the lengths till it adjusts. and we don't quite have a principled answer to that. But the reason I like this approach is actually the following. The idea of using relaxation and using fluctuations is critical to Nash's proof. And so this is, for me, the simplest cartoon in which you see the idea of relaxation, really the fact that we are kind of thinking about this PDE as a collection of geometric constraints, and these constraints have a kind of, you can relax these constraints to sub-solutions. And at the same time, the problem of degeneracy. So one of the things that's happening over here is that there are many possible diffusions that are achieving our goals, and we don't have a clean, really clean way of filtering through and saying this is exactly the right diffusion that'll solve our problem. But I like the elementary nature of this problem. I think for me, it's kind of the simplest example, like really this 2 points on the line is the simplest example where one sees kind of how probability theory, all I've done is do an ethos formula with a length squared. I mean, this is like, it's a kind of very simple thing, but it's kind of like, it's a critical piece of this puzzle. And one of the things I'm really looking for is to actually make this into an effective numerical scheme or an effective kind of principled model. So I feel like anyone, any probabilist who kind of thinks about stochastic control theory or something like that, this is an idea that's really waiting to be exploited. I just want to start it out with this because I really want to show you that there's a lot of territory over here to cover. And I hope my ideas, you can kind of see that I'm stumbling on the board, I'm not quite getting things. I hope that'll give confidence to the grad students, like, professors, like, they're just trying to figure out stuff. So I'm trying to figure out what is the right and the best stochastic control scheme to solve the graph embedding problems, and I don't know what it is. I have an idea. I have partial numerics with this idea. I don't have optimal theorems. I really feel like that's something where it's an easy start for a student to get into this problem and try to do something better than what we have. So there's kind of, let me kind of stop at this point because I just want to kind of give you one particular idea, the idea of relaxation and fluctuations. This idea becomes more and more sophisticated when one tries to do the PDE problems, but in some sense, it's the simplest place where you see probability in kind of at the technical level of trying to solve an embedding problem. And I think this is, for me, a good place to begin and kind of then move on to. So let me stop at this point. Thank you very much for your attention. Sorry, I feel that was a bit incoherent, so I'm not quite sure. Yeah, Arturo.
Thank you. Just to make sure I'm getting this right, the thing that you were looking was a mapping from B to R, to RD. You were looking for a mapping, and the mapping is the mapping that associates the ith component of the vector that you've built upon the R. What is the mapping? Well,
Okay.
so I'm getting that you have a bunch of components, and the index, which is associated with the vertex E, is associated to the limit of the diffusion. Am I right about this? You constructed that.
I think I very convincingly confused you. No, so, let's not use sight of the I's and J's, right? Let me just draw a picture. Let me say let me do stuff without the pictures, with the formulas, and then let's go back to your question so I can check that we're on the same page. So there are two different things. One is that you are trying to solve this algebraic system of equations, which says that I've got an embedding and the lengths between each of the edges must be given lengths. The way we're doing it is by shrinking the lengths and then kind of jiggling outwards. Right? So the picture is that I'm starting out with a sub-solution. So let's say I'm trying to solve this picture. So I'm trying to find a mapping from the abstractly defined, the graph, which is an abstractly defined square, into R2, so that each of these is of length 1. Okay, so that this is the solution that I'm trying to find. The way I'm finding the solution is by running a diffusion on these 4 points. I'm just drawing these lines over here for convenience. And so I'm trying to kind of write out a diffusion for each of these points. I'm trying to write out diffusion for each of these edges. Okay? And all I'm saying is that prescribing this diffusion So the form of the diffusion that I started out with was really, let's just do this in 1D. So the form of the diffusion I wrote out was, so it's this is, okay. So I'm just saying that writing out a kind of diffusion of this nature for something like this, which is vectorial, becomes kind of messy to write down because I have to prescribe the kind of noise at each of these guys.
Mm-hmm.
And the noise has kind of ij components because I'm sitting in 2 dimensions. So when you write out that diffusion, so kind of the equivalent was, so from an SD of this sort, you always get a covariance tensor. Everything is living within the covariance tensor. And I'm just saying that when I write out a multi-D version of this diffusion, the covariance tensor has that block structure. But I get constraints. In order to design my diffusion, I get constraints on that particular matrix, that covariance tensor. And the statement is that, like, if you can satisfy those constraints on that covariance tensor, you will get a diffusion that pushes you out so that all of your lengths are saturated as t goes to infinity. Is that picture? That's basically what I've been talking about.
Well, I get the construction of the diffusion. What
Yeah.
I didn't get was the final, let's say, the final product, which is a function. What I get correctly is, I think, what I
There's
get correctly
a
is
very good reason for that because I haven't proved a theorem that's converges.
okay.
So I'm just telling you that I got an idea, and I have done numerics with this idea, and I have not proved a theorem, and I would love for someone to prove a theorem. Okay? Is that clear? I hope that's clearer.
Okay,
Yeah? So the reason for kind of, like, look, I mean, one of the things for doing this in this way is exactly to kind of show you the elementary nature of the problem in terms of, like, it's really just length that we're trying to satisfy. And the way we build solutions to these, like the PDE, and the way we build solutions to these equations is through sub-solutions. So somehow the idea of working with sub-solutions is very, very kind of standard and basic in PDE theory. It turns out not so standard and basic in so there's an embedding community that studies discrete problems. There's an embedding community that studies the PDE problems, and they don't talk to one another. So in some sense, what we're trying to do, what I'm trying to give you a feeling for, is the possibility of tackling both of these problems together. And again, it's really just an idea. It's a stochastic control strategy. It requires a good theorem. And I don't know who will do that because my brain is full. But I'm just saying, like, there's an elementary piece of this. I was like, this should work. Somebody should know how to do this. A grown-up probabilist should be able to do it. But I'm not a grown-up probabilist. So, I'll leave it to you. Okay?
Well, we have another question.
Is that Carlos?
Well, it's actually 3 questions. The first one has to do with the structure of the SDE, of the stochastic differential equation.
Yeah.
You choose on the right-hand side to Wiener standard. What happens if you change the structure of the SDE?
So I don't know. So for me, this was really just the simplest model.
Oh, right.
And that's why.
Okay.
I liked very much the kind of elementary nature of it, and I liked being able. So a key piece for me was the ability to reduce things to an SDP. Because if I've got an SDP, then I know numerical methods. So that was kind of partly the rationale. But even that just came later. In some sense, I was really just trying. It's really been a process of convincing myself that kind of probability theory is kind of living within these problems. And so that was really, I was just looking for a minimal model. And so I didn't want to do anything more complicated. So I was just looking for the simplest model that would give me insight. So that's like, certainly one should be able to do more than this, but
Okay.
this is what we did. That's really it. Yeah.
The second question I have has to do with I think I heard you said something about the uniqueness of the rate of diffusion, right? That there's not a unique rate that yields that you can choose many different cases.
So what I really said is, really let's just do let's just do the 1D case, right? So what I'm trying to do is I'm going to get these points to kind of move apart and to dock so that on average, the length is going to decrease exponentially fast. So that's a choice. It's when you're kind of making a model, I would say this is my choice of the energetics. I just want like the simplest possible kind of. So I was choosing this to be, you know, this form. You could choose it to be whatever you want. And actually, this is kind of important in the sense that you can imagine that if you change the powers over here, if you make it like residual to some power alpha, it may not converge. So actually, somebody, it's a bit like, yeah, so in a sense, like maybe it's something like this, right? So if you think about stuff like the Feller diffusion, right? So I've got, let's say, dZt square root of, I hope this is correct, something like this. So if one looks instead something like this, so if you vary this power over here, you want to know if, you know, if you're going to kind of become extinct or not. And of course, there has been a lot of study in kind of how you change this power over here and you see what happens. So that's a complication that one can put in on top of this. But again, it was not, you know, for me, it really was all about fast numerical scheme. What I really wanted is a fast numerical scheme for doing the conformational diffusion. I don't feel like I quite had it because in some sense I couldn't quite resolve this problem to kind of, let's say, you know, really get it kind of completely right. There was stuff in there which is still kind of bothering me. But somehow the simplicity of the idea again was kind of what was appealing, that it doesn't matter what your diffusion is, on average you will push out. So the issue of non-uniqueness you raise is really related to how many degrees of freedom you have regarding your covariance tensor and how many constraints you have. The number of constraints is exactly equal to the number of edges. So there's a kind of topological complexity of your graph. And when you're trying to do this problem, you can so just do this very simple thing of trying to put the triangle into the line and the triangle into 2 dimensions. So my scheme cannot work in 1 dimension, but you can run such a diffusion, and at some point it's going to get jammed. So somehow what happens is that you always get exactly 1 equation on, or exactly 1 constraint on the kind of covariance tensor for every single edge. But the nature of your covariance tensor becomes bigger and bigger. Those blocks become bigger and bigger if you go into higher and higher dimensional spaces. So in some sense, like what you're trying to do is to find the minimal space into which you can embed and to make the scheme work there. You know, again, it kind of requires more knowledge in graph theory than I possess. I mean, everything over here seems to require more knowledge than I possess.
No, but
in some sense, there's a massive non-uniqueness, which is kind of one of the key pieces, or one of, I would say, the key problems in this class of problems. It's kind of like you have PDEs with many solutions, and you're kind of trying to define ensembles of solutions, or you have many possible diffusions that will get you to your goal, but somehow you want to make a kind of principled choice. I feel like people who study stochastic control have to have thought about this stuff carefully. And so that's not something I actually know the answer to. Again, it's the idea and a kind of partial execution. It's kind of waiting for, yeah.
And finally, sorry, but
Yeah.
thinking about
No,
this,
I love the questions, go ahead.
thinking about the solution to the problem of determining whether it converges or not.
Yeah.
Can you associate a Fokker-Planck equation to that SDE?
So on general grounds, yes, but like I feel like there's a conservation of difficulty over here. I feel like working with the SD or working with the Fokker-Planck, I don't see.
Well, I was thinking that perhaps if it happened that you could solve the Fokker-Planck equation and the solutions all lied on the same statistical family, then you could use some information geometrical results on, for instance, if the dynamics were geodesics, then you could prove convergence.
No, look, no, the point is well taken. The project never really matured to that level of sophistication. Let me actually kind of preempt something, and let me explain why. So somehow, when I actually began with the stochastic control strategy, what I was really trying to understand is to kind of, where I began, was really to kind of try to randomize Nash's scheme. And so, you know, I kind of began with that, and then I was like, I need a simpler problem. I need a simpler problem. I kept making my problem simpler and simpler until finally ended up with the problem of like, okay, can I put 2 points into the line? Okay, but one of the things that happened as we went there is that it kind of became more and more clear to me that there was a kind of natural class of kind of diffusions that one could seek over here. I'm not sure you need something as sophisticated as information geometry, but I think one of the things that does happen when you do this problem is that one of the things that you can really try to do is to design. So if you go into high enough dimension, one of the things that you can choose the covariance to be orthogonal to, see, you know, you can try to get the martingale term to be 0. This is actually a fact that we exploited and actually spoken about before, but you know, we kind of designed a model for RMT that does that. So if you're in high enough dimension, there's a kind of elementary thing that you can try to do, which is to put your fluctuations in such a way that the martingale term vanishes. So you really have this stuff which is jiggling around, but the lengths are actually increasing deterministically. And so it's not something fancy like information geometry, but it actually does use the graph, uses orthogonality. And the real kind of complicated piece is, in some sense, in the nature of these constraints. So it turns out, so you know, there's a kind of the nature of these constraints for different graphs as you get down with it. I couldn't find a clean enough system there. And so somehow I feel like if one is to dive into that problem, the kind of best possible diffusions would be diffusions that do not have a martingale term, and where somehow there's a clear way of seeing what the nature of these SDP constraints is. So, you know, I'd be very happy to send you kind of partially written kind of ideas in this area, which have kind of not been fully worked out. But I think that's the level. I wouldn't try to make it too fancy. I think in some sense, the graph embedding problem is important because of its minimality. And for the same reason, I think the stochastic control strategy should also be minimal so that you can kind of do either a fast algorithm or you can prove an interesting theorem. So that's what I would say. Okay, thanks.
Great. So we'll have plenty of time during the week to ask more questions. So now let's thank Govind again for the first lecture.
Thanks very much.